Okay, let's start with the conceptual system block diagram power architecture for the second approach that based on the uniform voltage distribution maximum power tracking control or group tracking UVD. The first architecture we call battery dominated power architecture. That for this example we have three channels for three sourcing voltage V1, V2 and V3 are controlled to have uniform distribution by isolated controllable converter number 1, number 2, number 3 to control signal VC1, VC2, VC3. In order for this control system to work together, the system controller requires 6 feedback variables, which is the sourcing voltage V1, V2 and V3, the battery voltage V bus, the system's sourcing bus current I bus, and the battery charge current I back. This chart shows the system block diagram for the system controllers of the battery dominated power architecture with uniform voltage distribution maximum power tracking. Distributed input voltages V1, V2 and V3 are fed back for achieving their equal sourcing voltage to the uniform input voltage distribution controller. Furthermore, there are two basic functions of this control. Under non-maximum power tracking mode, which is belong to the battery charge controller, to be able to regulate the battery current I back at the preset commanding reference, or controlling the battery voltage according to the voltage temperature profile. Allow the battery to charge at the trickle charge rate to limit the voltage of the battery according to the temperature. Another function is for maximum power tracking that involves two control blocks. One is called maximum tracking controller, and another one is input voltage regulator. These two functional blocks provide maximum power tracking to the controlling voltage VC. Whenever the battery charge controller fails to regulate its charging current I back to the target, it's going to cause the diode D to be reversed by arc, and as a result, the MPT controller and input voltage regulator will work together with the uniform voltage distribution to track the system peak power. This chart shows simulation results of the battery dominated power system response. Regardless of the mode of operation, whether it's in the input voltage regulation mode, which is corresponding to maximum power tracking mode, or active battery current regulation, which is considered as non-maximum power tracking mode. In these two major modes, voltages across three power sources are uniformly distributed as shown in three overlapping traces on the top plot. As you can see that when they are in the maximum power tracking mode, they exit low frequency ripple in this simulation is about 20 Hz. This little ripple is required and intentionally inject into the system in order to allow the maximum power tracking mode to work efficiently. This chart is another chart showing the simulation of the battery-dominated power system response. This chart emphasizes the operation during maximum power tracking mode, that the battery charge current is regulated according to whatever the power sources can offer. In this format of control, the maximum power tracking or group track uniform voltage distribution able to provide the maximum current available, which is in this case only 53.6 amp, to charge the battery. The voltage across three power sources still uniformly distributed or equal, as shown in the three overlapping traces on the middle plot. During this maximum power tracking mode, the battery charge command had been set significantly above 53 amp. This chart shows the simulation emphasizing the operation change due to the change in the power source characteristic that lead to the two different peak power points. One is at 1357 watt and another one at about 1170 watts. The purple trajectory show the transition between these two peak power points. This purple trajectory is extracted from the same time domain simulation that use the total sourcing power and the distributed sourcing voltages, process into the XY mode and plot the power and voltage trajectory overlaid on top of the DC characteristic power versus voltage of these three distributed power sources under two different sourcing circumstances. One, when the sourcing voltage are identical at 60 volts, which is shown in the lower curve, and the other one when the sourcing voltage of power source number 1, number 2, and number 3 have different voltage to be 80 volts, 60 volts, and 50 volts respectively. The PSpice simulation verified that the GTU with the MPT control is able to track a new peak power point of 1357 watt. That is higher than the previous peak power point of 1170 watt. An increase open circuit voltage of power source number 1 from 60 volt to 80 volt leads to the increased peak power. The tracking efficiency is 98.8%, which is very much acceptable and consider that is sufficient.